This section examines joins purely from a performance tuning perspective. An inner join is an intersection between two tables. The join is usually performed between two referential integrity keys in those two tables. Intersections are the most efficient types of joins because they match records between two tables based on equality, an equal sign. The queries on the slide are the same. It joins the employee and department tables based on the primary and foreign key link, which is a one-to-many relationship. To determine an employee's department name, you compare the value in the department number column in the employee table with the department number values in the department table. The relationship between the employee and department table is an equijoin. That is, values in the department number column on both tables must be equal. We also need to qualify the names of the columns in the where clause with the table name to avoid ambiguity. Without the table prefixes, the department number column could be from either the department table or the employee table. It is necessary to add the table prefix to execute your query. A self-join is a special type of intersection where records on multiple hierarchical levels stored in a single table are returned as a hierarchical structure. The example displays the employee name and employee number along with their manager's last name and manager number. While an inner join returns an intersection between two tables, an outer join returns the opposite of an inner join. It returns all records in one table, which are excluded from the other table. The query above displays the employee name and employee number along with their manager's last name and manager number. It also displays all employees who have no manager. A cross-join is a Cartesian product, joining every record in one table to every record in another table, regardless of any meaningful referential integrity connection of keys. Obviously, cross-joins will be slow, depending on the number of records in both tables, relative to each other, and in total number of records. The query returns all employees in all departments, regardless of any employees to departments relationship. In other words, every employee is returned with every department, regardless of who belong to what department. Let us have some actual samples of joins from our department and employee table. The where clause specifies how the tables are to be joined. E the department number equal to D the department number. Because the department number column is common to both tables, it must be prefixed by the table name, or in this case, an alias, to avoid ambiguity. Qualifying column names with table names can be very time-consuming, particularly if table names are lengthy. Table aliases help to keep SQL code smaller, therefore using less memory. Let us run the examples. The first query returns 14 rows. Both queries gives us 14 rows. In addition to the join, you may have criteria for your where clause to restrict the rows under consideration for one or more tables in the join. Here are some examples. Another example. They have the same result. Here is an example of a self-join from the previous slide. It displays the employee name and employee number along with their manager's last name and manager number. Here is an example of an outer join. Other than the employee and manager information, it also displays all employees who have no manager. So let's run. So King, who has no manager, is also displayed. Cross-join produces a result set which is the number of rows in the first table multiplied by the number of rows in the second table. This kind of join is not that useful. So it returns 56 rows. How do you get 56? Let us try to run. How many employees are there? How many rows? There are 14 rows. And in the department table, there are 4. So 14 times 4 will give us 56. The most important factor for performance tuning joins is minimizing the number of tables in a join in all types of database models.